Hi, so I was unwell on Tuesday because I had a surgery on Monday. So that's why I postponed that lecture to like that problem solving session to this Thursday. So I'll just take a very short session and I'll upload the video. So this for week 6. Okay. So what was discussed in week 6 was one sec. Yeah. So two topics were discussed. One was some examples of LP linear program and uh, duality, weak law and strong law. Strong law. Okay. So examples of LP is like a problem that you can model as an LP, and duality was basically uh, so duality for linear programs. Basically, there is some linear program of this form: C transpose X, Ax equal to Bx greater than 0, and we say there is a dual of what is there on the left side, and its dual is of this form: max y B transpose y A transpose y less than equal to C. Okay, so this is the dual of this. So this is called the primal, and this is called the dual. So here what you have is the primal is on a different set of variables, the dual is on a different set of variables, but the parameters of both the problems A, B, C are shared. This is shared between the, like, this is an observation, right? An observation between the primal and dual. Okay, but why is this an interesting thing? Like, how did we get this dual? Why is it important? It's important because there's this two interesting properties of weak law and strong law. What the weak law says is if fp, this is the feasible set of primal, and if d, let's say, is feasible set of dual, then C transpose X is greater than equal to B transpose Y for all X in Fp and Y in Fd. This is the weak law. The weak law is saying a primal solution always upper bounds the dual solution. The dual solution lower bounds the primal solution. Okay, so if you have a point x which satisfies the constraints of the primal, then the primal objective will always be that particular primal objective. Let's say I have some x hat which solves x hat solves the primal means x hat is in FP, it's in the feasible region, it satisfies all these constraints of the primal. And if I compute the C transpose x hat, which is the objective value, this should always be greater than uh, B transpose Y for all Y in the feasible region of the dual. Okay, just same thing I have basically written, nothing different. Just to try to explain it slightly and slightly different. Okay. And the other way also you can do. But the strong law is in some sense a stronger statement, like it satisfies this but something more also. That's why it's called the strong law of duality, which happens in the case of a linear program. So the strong law says that if uh, yes, so the strong law says that the solution of both these are equal, the optimal value. Optimal values of primal and dual, if they exist, are equal. Finite. Okay, this is the strong law. So that means if P star is argmin, not argmin, sorry, minimum x in FP C transpose x, then this is equal to some d star which is equal to the minimum value of y in FT B transpose y. Okay, this is the strong law. So let's look at some question. Okay, so let's first let's do an example of linear program called the network flow problem. So you have a network of n nodes and directed link connecting each pair of nodes. Okay, each pair of n nodes is connected by a directed link. So you have that you have this data that what exactly data you want to measure. You have some variable basically xij, which is the flow from node I to j, and there is a cost associated with the flow. So to make xij amount of flow, cost of xij flow is equal to cij xij. Okay, cij are constants. So when you are, so there is a component called cij associated with each link, and that constant times the how much flow you are allowing via xij, that is the cost of xij flow. So that means the total cost c is equal to summation cij xij ij equal to 1 to n, right? Okay, so this is the cost, and now there are some constraints. Constraint is lower bound on flow on each link lij. So you can only you have to have at least lij flow in each link. Okay, this lij is greater than equal to 0, and upper bound, that is uij. This should be greater than equal to lij. You can't have more than uij. And also each node has an uh, external supply bi. Okay, bi is in r. So which means like there is a node, let's say this is in our network, there can be some external supply bi, which if it is positive that means it is going into the node, but there is no like as such connection from anywhere, it's just going into that node. And if it is negative that means it is going out of that node. Okay, so and it is given that uh, there are n nodes, right? So 1 transpose b is equal to 0, and this is a vector of ones, 1 1 like that, of size n. So that means this summation bi I equal to 1 to n is equal to 0. That is, how much is flowing into the network is the same amount that is flowing out of the network. Okay, because there will be some positive and negative BIs. So we need to define an LP to minimize C, total cost. So that means our LP will be so simple thing. So to write whatever we discussed right now. So we want to minimize this. J equal to 1 to n, subject to bi plus xij. Okay, that is like let's take one node I. This node, whatever is coming into the node should go out of the node. Okay, so bi is coming into the node and xij is I should write xji, right? Because I said flow from node I to j. So bi is coming into the node, xji is coming into the node, j equal to 1 to n, and what is going out is xij. Sorry, this should be just j. J equal to 1 to n. This should be equal to 0. Okay, this is like balancing flow constraint. Okay, for this is for all. Okay, let me this here a bit. This is for all I from 1 to n. So for each I you have this, so you have n balancing for flow constraints. In each node you are balancing the flow, whatever is coming in is going out. So bi is coming, xji is coming from each j, and xij is going out of each from going out of I to each of the j. But we also have some more constraints, which is some inequality constraints, which is the lower bound and upper bound. So xij is then equal to uij greater than equal to lij. This is for all I j in 1 to n. Okay, so this summarizes everything, right? We have the balancing flow constraints and the upper and lower bounds on the flow, and this is the LP you need to solve to minimize the total cost, satisfying the flow. So this bi is like summarizes the how much demand or something like this there. Which you have to like how much supply and demand is there. Okay, so I with bi greater than equal to 0, or basically bi greater than 0, are supplying through the network, and 0 flows out of the network. Si. So, and we said that summation bi is equal to 0, so the flow is balanced in this case. But we need to adjust the flow in the network of our end nodes such that the cost is minimized. So that is what this LP will solve. Okay, this is an example of a linear program. Let me now do a question related to dual. So we had C transpose X. Let's say this is the thing. And we have okay, we need to show one is to show 2 is dual of 1. So the question, show 2 is dual of 1. Okay. So what do we know? We already studied the dual, right? But there is something different here. What we had been like what was shown to us was, for this program this is the dual. Okay, let me take this over there. This is what we know. So here you have an inequality constraint, here you have an equality constraint. So we need to convert this to this form, and then we'll get the dual for this form, and this dual we need to show is of the form of the second equation. So here we have an inequality constraint, and to convert it into a equality constraint we need to add some slack variables, and we also need to make sure that all the variables are positive. So I have ax greater than equal to b. Check and write as ax equal to b plus z. Z is in, say, Rm. So that means my A is Rm cross n, B is Rm, C is in Rm, and X is in Rm. Okay. So ax minus z equal to, okay, here z is greater than 0. If it's greater than equal to, I can add a positive uh, vector to this. Okay, but now here I need some matrix times my variables. So how do I convert that? Let's say AI is a row of row vector of A. Okay, A is a row vector of A. So my A is basically like this: A1 vector, A2 vector. Like that, I have m rows, am, and each of ai is in Rn. Okay, that's how it is m cross n. So this part I can write it as, I will construct a yeah. So basically, if you look at one, no, this is a vector, and this is also a vector. So you look at one element of that vector. One element will be like bi is equal to ai x, right? Because this is a row vector and x is a column vector. And let me, okay, I'll call this as ai transpose. Okay, yes. So now I ai transpose x plus zi. This is an element of bi. So that means, how do I write it in matrix notation? I have some a1, a2, like that till am, and I'll have this minus z, sorry, I'll have here minus 1, 0, 0, 0, 0, and here minus 1, 0. So I have some sort of an identity, like all the diagonals are minus 1. Times x1, x2 till xn, and z1, z2 till zm. Okay, so these are m columns. So this is m cross m, this is m cross n. So basically this is of this form: a minus I and x z is equal to b. And my x is greater than equal to 0, z is greater than equal to 0. Okay, and this is m cross m plus n. matrix. So now I have it in this form, right? I have some ax equal to b. This I can call as some a tilde, and um, this I can call as some x tilde. Okay, and I can have some c, like let c tilde equal to c1, c2, cn 0 0 0. So it is of some c and 0. So I can have, so I have c transpose x tilde ax tilde equal to b x tilde greater than equal to 0. Okay, so now I have this form. Minimize x tilde, and I know the dual for this. Dual is b transpose y max y such that a transpose y is less than equal to c. So here also it is a tilde. So I'll have a tilde transpose y is less than equal to c tilde. Now I need to show this is equivalent to the second problem. So I'll expand my a tilde and c tilde to see how it is. So a tilde is basically a my a and minus I transpose y less than equal to c and 0. So that is a minus I y less than equal to c0. So this you can write as ay a transpose, a transpose y less than equal to c and minus I transpose y less than equal to 0, and this is basically y greater than equal to 0. So that means my optimization problem, this is max y b transpose y a transpose y less than equal to c and y greater than equal to 0, which is same as the second, right? B transpose y transpose. So this is the dual for this problem with inequality constraints. Okay, yeah, so that's all we're going to discuss. Thanks.